Dear students, welcome to all of you. Now we discuss numerical practical problem 21 Gaussian quadrature rule by C programming. Gauss quadrature or Gaussian quadrature rule or method. Write a C program to evaluate the definite integral for the function fx equals to uh, 1.5 plus p into sine cube x whole to the power minus 3 by 2 within the limits of integration 15 degree and 60 degree, correct up to 6 decimal places by the 5-point Gauss quadrature formula, where p equal to r plus 1 by 20 and r is the last digit of your C roll number. First we discuss about Gaussian quadrature formula. This an n-point Gaussian quadrature formula constructed to get an exact rule for polynomial of degree less than or equal to 2n minus 1 by a suitable choice of intermediate nodes xi. Hence, it is an open quadrature rule. And the corresponding weights wi for I equal to 1, 2, n within the integration limits minus 1 to 1 usually. So, integration minus 1 to 1 fx dx approximately equal to w1 fx1 plus w2 fx2 plus plus wn fxn. And in this formula, wi and xi, I equal to 1 to n, are symmetrical with respect to the middle point of the range of integration minus 1 to 1. If we choose wi and xi, I equal to 1 to n, in such a way that the error term e, which is equal to the exact value of the integration minus the approximate value of the integration summation I equals to 1 to n wi fxi is equal to 0, error term equals to 0 when fx is a polynomial of degree less than equal to 2n minus 1. So when n equal to 1, so fx equals to degree 1. So n equal to 2, fx equal to n equal to 1 to 2n minus 1, 2n minus 1. So less than equal to this. So fx equal to 1 x square x to the power 2n minus 1 in the above equation 1. In the above equation 1. In the above equation, sorry, in this above equation means this the above equation is 2. This is the equation 2. Equation 2. In the above equation 2, this error term e equal to 0, integration put fx equal to 1, and then this w fx equal to 1, w1 fx1 equal to this, we get this w1 plus w2 plus wn equal to 2. And when fx equal to 1, sorry, fx equal to x, fx equals to x, that is when n equal to 1, 2 minus 1 is equal to 1. When n equal to 1, 2 in minus 1, that is equal to 1, x to the power 1. When n equal to 2, 2 to 4 minus 1, 3. And this, so w1 x1 plus w2 x2 plus wn xn equal to 0, and w1 x1 square w2 x2 square plus wn xn square equal to 2 by 3. And lastly, w1 x1 to the power 2n minus 1, w2 x2 2n minus 1 plus wn xn 2n minus 1 equal to 0. The above system has 2n equations. This 1, 2 up to 2n equations, and 2n unknowns. This is w1, w2, wn, and x1, x2, xn. So we can solve this system, but it is very difficult to solve for higher order of n, and and then solving for n equal to 1, we get w1 equal to 2 and x1 equal to 0. If n equal to 2 and uh, 1 w1 equal to 1, w2 equal to also 1, and x1 equal to plus 0.57735, and x2 equal to minus 0.57735. When n equal to 3 and w1 equal to minus w1 equal to 0.5555, w2 equal to 0.888, and w3 equal to, here w1 and w3 are equal, and w2 is this. Here x1 is this minus 0.77, and this x2 equal to 0, and x3 equal to plus 0.77, and so on. Here we provide a list up to n equal to 10 point quadrature. Normally we use the 5 point quadrature, Gaussian quadrature rule. This and higher orders of n, that is n equal to n equal to 11, 12, and so on, so on, so on. But it is very difficult, and it is the very difficult to discuss here. And for this figure for Gaussian quadrature, this is the 2-point Gaussian quadrature formula. This is the function y equal to fx, this is the red curve, and this is the minus 1, this is the point minus 1, and this point 1, this point 1. So we integration minus 1 to 1 fx dx. Here this x0 and x1 are two intermediate points of minus 1 to 1, and this corresponding fx0 and fx1 and corresponding weights for 2 points, w1 equal to 1 and w2 equals to also 1. So formula is w1 fx1 plus w2 fx2, and this is the area of this trapezium, of this type trapezium. This corresponding Gaussian quadrature nodes this x0 and x1, and this within this limit of integration minus 1 to 1. So it is an open type integration. This that transformation of the limits of integration of AB, if other than minus 1 to 1, if the limit of integration a to b fx dx, then we use the following transformation: x equal to b plus a plus b minus a bracket into t whole divided by 2, where t is the limits minus 1 to 1. So this integration a to b fx dx becomes this b minus a by 2 integration minus 1 to 1 a capital A b plus a plus b minus a t whole divided by 2 dt. And correspondingly the formula is this, the approximate formula is this: b minus a divided by 2 w1 a ft1 w2 ft2 plus wn ftn, and this. Now this is the problem. First we define this float pi is constant variable, constant float pi is equal to 3.14, and this, and float a function, this given function is this. So these arguments are float a, float b, float t, and float p. Here float x equal to t into b minus a plus b plus a divided by 2, because here the limit of integrations are 15 degree and 16 degree, so not minus 1 to 1 degree. So we change this x to t by substitution, this substitution, this b minus b plus a bracket b minus a into t whole divided by 2. And this function float variable a b p w 50 t 50 and some integer variable in I and r, and print enter the value of r, the last digit of your roll number, and p equal to r plus 1 by 20, this, and values of the lower limit and upper limits. This enter the lower limits in degree, here degree 15 degree, and the upper limit is 60 degree, and the this change degree to radian by this revise this a pi into a by 180 and b equal to pi into b by 180. These steps. Enter the number of ordinates or nodes. Here in this question, this 5-point Gauss quadrature formula. So here nodes are x0 x1 x2 x5, so nodes equal to n equal to 5 here. If there is a question, if there is a 4-point Gauss quadrature formula, then 4 points quadrature, then n equal to 4, put n equal to 4. So this is the formula, apply this. Now we use here the switch statement, this in if you put n equal to 1, then case 1, n equal to 2, then case 2, and n equal to case 3. Here n equal to 5, because there are 5-point Gauss-quadrature formula. So in n equal to 5, and then t1, t2, t3, t4, t5, and corresponding w1, w2 are equal, w5 are equal, w2 and w4 are equal, and w3 equal to this, and break. And default printf due to limitation of our present scope. Here not only for n equal to 5, n equal to maybe n equal to 6, n equal to 7, and so on, for higher positive integers also. But a limitation of scopes, for the present scopes we enter any integer from 1 to 5. Where the nodes are, this corresponding value of nodes, this t1, t2, t5, and corresponding weights are this w1, w2, w5. Initial sum equal to 0, and this for I equal to sum plus wi plus f of a b t p. This is the new sum, present sum, and this equal to the previous sum, initial sum 0 plus wi into this. Actually this formula this b minus a by 2 w1 ft1 plus w2 ft2 and plus wn ftn. And so sum equal to b minus a by 2, because this the sum is b minus a by 2. Correct value of the required integration is the 6 decimal places, so 10.6 here, correct up to 6 decimal places. And save this program and compile and run. So enter the value of r equal to say 5. Enter the lower limits in degree, say 15 degree, and this upper limit is 60 degree, and this is the enter the number of coordinates for nodes. Here the 5-point Gauss quadrature formula, so we put here a number of nodes is 5. And so here apply 5-point Gauss quadrature formula. This is the formula, this a b minus a by 2 w1 ft1 and so on so on. And where the nodes are t1, t2, t3, t4, t5, and the corresponding weights are w1, w2, w3, w4, w5. The value of the required integration is 0.396760, and this is the solution of this Gauss. Thank you for watching this video.